Hello everyone! Today is another exciting day in the world of calculus lessons. Today we're going to talk about the first fundamental theorem of calculus, which goes hand in hand with definite integrals. So as you can hopefully tell by the name, Fundamental Theorem of Calculus, this is really exciting and really important. So please take good notes. Let's get started. Alright, so let's begin with definite integrals. We talked last class a lot about definite integrals and what they were, and we actually evaluated several definite integrals using geometric methods. And the idea was that any definite integral that I asked you to evaluate last time, if we were to sketch it, that our pictures were always ended up being a function was a straight line or was a semicircle, something that we were able to use area formulas that we already knew, like area of a triangle or trapezoid or circle, semicircle. And so because of that, we're kind of limited to what we could really evaluate, which integrals we could really evaluate their definite integrals. And so today we're going to talk about what happens if you have a curved function such as this. And if I want to find the area underneath the curve from A to B of this region A, then how do we do that? Well, I certainly wouldn't be able to draw in a triangle, and so I am limited to not using a geometric method, but to come up with a different method, and that's what today's lesson's all about. So let's go through the formal definition first of definite integrals. The definite integral is the area of a region. So when we talk derivative in the beginning of the year, I have tried to pound it in your head that derivative is synonymous with slope. Well, now I want you to understand that integral is synonymous with area. Okay, so if f is continuous on the closed interval a to b, then the area of the region bounded by the graph of f of x and the x-axis and the vertical lines x equals a and x equals b is given by the integral from a to b of f of x dx. Okay, so now that we reviewed what a definite integral is, and we have a picture in our mind, we now need a method for evaluating that definite integral. And that's where the first fundamental theorem of calculus comes in. It is a method for evaluating this definite integral. So if we go ahead and decide that capital F of x is the antiderivative of f of x, then we can say this: the integral from a to b of f of x dx is, so that's exactly where we left off with the graph and the definition of the definite integral. Now, how do we evaluate this? Well, this is what it says. We're going to do f of b minus f of a. Okay, so let's think through exactly this theorem that we just wrote down. All right, so we have this exciting new theorem. What is it telling us? Well, it's saying if we want to find the integral from a to b, the area under the curve from a to b, the closed interval a to b of this graph f of x, then how do we evaluate that? Well, we take the antiderivative of the function and we evaluate it at b, and we take the antiderivative of the function and we evaluate it at a, and then we subtract them. So that's what this rule is telling us. That's what the first fundamental theorem of calculus is. Now, there are some people who don't really like the capital and lowercase f, and so you'll also see it written like this: the integral from a to b of f prime of x dx is equal to f of b minus f of a. And this is saying the exact same thing. Okay, so it's saying, again, the integral from a to b of, or the area under the curve between the closed interval a and b of this function of this graph is equal to the antiderivative of f prime of x is f, but we're evaluating at b first of all, minus the antiderivative of f prime is f, but evaluated at a, and subtract them. Okay, so we're going to practice using this theorem to evaluate definite integrals with several problems tonight. But first, let's just kind of recap our steps, and then we're going to get started. Okay, so the first one that we're going to evaluate is the integral from 0 to 4 of 4x minus x squared dx. So we're going to go follow through those 4 steps that we just talked about. First was take the antiderivative. Okay, so we're going to take the antiderivative of 4x minus x squared. So following my rules, I copy down the constant. X, the integral of x would be x squared over 2 minus x to the third divided by 3. Okay, and then we write it like this. We're going to evaluate this from 0 to 4. That's usually how we show it. All right, so go ahead and clean this up if you want. That 4 is like over 1, so of course this cancels into a 2x squared minus x to the third divided by 3, and we're evaluating this from 0 to 4. Now we don't need a plus c because we are doing this definite integral. All right, now the second step was to substitute in the upper bound. So when we evaluate this, we plug in the upper bound, which obviously is 4. All right, so we're plugging in this 4 in for x everywhere where we see it. Okay, so we're going to have, and I'm going to put this in a bracket, 2 times 4 squared minus 4 to the third divided by 3. Minus, now we do our lower bound into the same exact thing. So 2 times 0 squared would be 2 times 0 minus 0 over 3. All right, so on the left-hand side, let's kind of clean this up a little bit. We have 2 times 16 would be 32 minus 4 cubed is 64 over 3. Minus, well, this is obviously just going to turn into 0. Okay? Okay, so obviously we need to get a common denominator here in this first bracket in order to subtract these. So I'm going to rewrite 32 as 96 over 3. So now with the common denominator, I can subtract those numerators, and I get 32 over 3, and that is my final answer. Okay, second one. The definite integral from 0 to 1 of 1 plus x to the 4th over 2 minus 2x to the 9th over 5 dx. All right, so again, first step is to take the antiderivative. So the antiderivative of 1 would be 1x plus, let's see here, this in front of here is 1/2. So we have 1/2, and then I'm going to go ahead and do x to the 5th divided by 5 minus, here I have 2/5, and then x to the 10th divided by 10. And we're evaluating that from 0 to 1. All right, so let's clean this up one more step. So I'd have x plus, I'm going to clean it up to x to the 5th over 10 minus 2 is going to cancel into this 10 and leave a 5. So I'm going to have, let's see here, x to the 10th over 25. And again, from 0 to 1. Okay, so now we're ready to plug in those bounds. So when I plug in the upper bound, I get 1 plus 1/10 minus 1/25. Minus, this is just going to be 0, plus 0 over 10 minus 0 over 25 is 0. All right, so let's get a common denominator over here on the left-hand side. So my common denominator, I believe, would be 50. That would be the smallest number that all of those would divide into. So here we have 50 over 50, 50 over 50, plus this would be 5 over 50 minus 2 over 50. And so I should be able to add those. That would be 53 50ths. And that is my answer. Okay, from a couple of videos ago, when we are doing the integral of a quotient like this, remember there is no product or quotient rules. There's no rules like we had with derivatives. Instead, you have to go ahead and split this up using what we know about fractions. So we're going to go ahead and split this up and rewrite it as the integral from 1 to 2 of n to the fourth divided by n squared would be n squared, and then plus 1 over n squared I'm going to write as n to the negative 2, and of course dn. Okay, so now I'm ready to go ahead and follow through on my definite integral steps. And so first of all, I take the antiderivative of each of those, so that would be n to the third over 3 plus n to the negative 1 over negative 1, and of course that's from 1 to 2. Okay, I'm going to take one more step just to kind of rewrite this to make it look a little bit more like I like it. So I'm going to keep the first one, n to the third over 3. But then what does this turn into here? All right, well, I know n to the negative 1 is the same as, hopefully we're all saying, 1 over n. And then divided by negative 1 is just going to really negate it. So I'm going to write this as minus 1 over n. And again, that's from 1 to 2. All right, so now I'm ready to go ahead and evaluate by putting in my bounds. So as I put in the top bound, I get 2 cubed, which is 8 thirds minus 1/2. Minus, now I'm going to put in the lower bound. So as I put in this lower bound, be careful, we have 1/3 minus 1 over 1 is 1. Now what I've done here, hopefully you're recognizing this and following along. It's helpful if you put the upper bound in your first bracket, then subtract, and then put your lower bound in your second bracket. Keep these neat. Keep them organized. Evaluate each one individually and then subtract their total. So 8 thirds minus 1/2. Again, I need a common denominator. So I'm going to go ahead and get a common denominator of 6, which would make this, let's see here, 16/6 instead of 8 thirds. And here that would make this 3/6. Okay, so now I can subtract those here and I would get 13 over 6 minus, all right, 1/3 minus 1. If I go ahead and try and get that same common denominator of 6, that might be helpful. So this would be 6 over 6 and this would be 2 over 6. So if I subtract those, I get a negative 4/6. And so obviously that's going to be adding, and I end up with 17/6 is my answer. Okay, I want you to go ahead and try this one on your own. Get it written down. Now notice here that we do have a squared. Remember, there is no chain rule. There is no product rule. You are going to need to rewrite this before you take the antiderivative. That means you're going to need to write it twice and FOIL, then take the antiderivative, then plug in your bounds, and then evaluate. So go ahead and pause the video, please, and try that on your own, and then come back to me and see if we agree on our answers. Okay, so as we compare our answers, once again, I started with writing my binomial squared twice, and then I FOILed it out. Okay, and then I took the antiderivative. So the antiderivative of each piece using my antiderivative rules from over the interval of 1 to 2. Okay, I just cleaned it up, one quick step here, and divided the 8 and 2 to clean that up. Then I went ahead and plugged in my 2. So 2 cubed was 8 thirds minus 4 times 2 squared, or 4 times 4 is 16, plus 16 times 2 is 32. This, of course, cleans up to be positive 16. Okay, so as I move forward, I'm going to use the positive 16. Minus, now I go ahead and plug in my lower bound. So 1/3 minus 4 times 1 is 4, plus 16 times 1 is 16, and again, this cleans up to be a positive 12. So I needed a common denominator, and I can clearly see that for both of these, the common denominator is going to be a 3. So 8 thirds comes down, plus, remember I said that I cleaned this up to 16? 16 times 3 is 48 thirds. Minus, again in brackets, 1/3 plus, clean this up to be 36 thirds, and then I went ahead and added those fractions, added these fractions for each of these to get 56 thirds minus 37 thirds, subtracted those, and got 19 thirds as my answer. Okay, looking at number 5, the integral from 1 to 4 of 3 plus x square root x dx. Okay, I cannot stress enough how important it is to rewrite before we get into this. And so if I rewrote this, I'd have the integral from 1 to 4 of 3 plus x times x to the 1/2. Well, hopefully I know that x times x to the 1/2. When you are multiplying powers, you add exponents. Multiplying powers with the same base. So I'm going to rewrite this one more time as the integral from 1 to 4 of 3 plus x to the 3/2 dx. Now I'm ready to go ahead and evaluate that definite integral. So first of all, take the antiderivative. So that would be 3x plus, let's see here, I'm adding 2/2 to the 3/2, so I would get x to the 5/2, and then divided by 5/2, which is the same as times 2/5. And of course, I'm evaluating that from 1 to 4. Okay, so now let's go ahead and plug in my upper and lower bound. So first of all, my upper bound is 4, so I'd have 3 times 4, which would be 12, plus 2/5 times 4 to the 5/2. Well, I'm going to write that as the square root of 4 all to the 5th power. Okay, minus, now go ahead and plug in your lower bound. So 3 times 1 is 3, plus 2/5 times 1 to the 5/2 is just 1, so I'm going to leave it like that. All right, let's definitely clean up this left-hand side. So 12 plus 2/5 times the square root of 4 here is 2 to the 5th is 32. So I'm multiplying this times 32, or 32 over 1. Minus, all right, let's get a common denominator here. Okay, so I'm going to rewrite this as, let's see here, I'd have 15/5 plus 2, which would be 17/5. All right, so over on this side, obviously I need another common denominator of 5, so I'm going to write this as 60/5 plus 32 times 2 is 64/5 minus that's 17/5. And so 60 plus 64 would be 124/5 minus 17/5. Okay, and as I subtract those, let's see, I would get 107 over 5. And so that is my value of that definite integral. Okay, next up I have 6 basic trigonometric integrals. And I know right away you're not very happy that you're being asked to memorize more things, but if you take a look at these, hopefully you'll realize that if you know the derivatives of your trig functions, that the integrals are going to make sense to you. Okay, because you already know them going forward, so now I'm just going backwards. So it should make sense that the integral of cosine x dx is sine x plus c. Why does that make sense? Well, because then I know that the derivative of sine is cosine. It should make sense that the integral of sine x dx is negative of cos x plus c. Why does that make sense? Well, because I know the derivative of cosine is negative sine. So now the integral of sine is negative cos. Okay, so now the integral of secant squared x dx is tan x plus c. Again, the derivative of tan was secant squared, so going the other way. Okay, continuing on, the integral of secant x tan x dx is secant x plus c. The integral of cosecant squared x dx is negative cotangent x plus c, and the integral of cosecant x cotangent x dx is negative cosecant x plus c. Okay, so now that you've been given these trig integrals, I can use them and practice doing some evaluating of definite trig integrals using these rules. So first step would be to take the integral of sine theta d theta. So if I look at this, I'm going to go ahead and say the integral of sine theta d theta would be negative cosine theta, and I'm evaluating this over the closed interval pi to 2 pi. And so now I'm ready to go ahead and plug in my upper and lower bound. So I'd say negative cosine of 2 pi minus negative cosine of pi. So this was the upper bound and my lower bound. All right, so if I think about cosine of 2 pi, all right, here's my cosine curve. Cosine of 2 pi is right here, and that would be at a height of 1, so this would be negative 1 minus, all right, negative of cosine pi. Well, pi is right here, right here, and so that would be right down here, and that would be negative 1. So I'm talking a negative of negative 1. Which of course is going to be positive 1. So I have, there's lots of negatives here. So I have negative 1 minus, this is going to become positive 1. So negative 1 minus 1 is negative 2.